In this video, we're going to learn about the strengths of bonds and how energy plays a role in how bonds are formed and how bonds are broken. Everything in this video is going to be heavily dependent on Coulomb's law, so let's take a minute to review that. Remember that the force that pulls charged objects together depends directly on the charges of those objects, so that's Q1 and Q2 in this equation, and inversely on the square of the distance between those objects. Energy is force times distance, so if we multiply K, Q1, Q2 divided by d squared times d, you cancel out one of the d's. So the important thing for us is that the energy required to overcome the force that pulls attractive objects to each other will be proportional to the product of the charges of those two objects and divided by the distance between them. So there's an interplay between those two quantities. How much charge are in the objects that are attracted to each other and how far apart are the objects. That's the D part. First of all, let's look at covalent bond energy. Well, covalent bond is formed when two nuclei are attracted to a shared pair of electrons that's in between them. So the attraction is between the nucleus, represented by the gold positively charged sphere here, and the electrons, which are the little blue negatively charged spheres in this little picture. If you're going to break that bond, that's going to require that you overcome that attractive force between the nucleus, or the core of the atom, and the valence electrons that were making the bond. So you may remember from an earlier video this diagram that has internuclear distance on the horizontal axis and the energy on the vertical axis. And the sweet spot down at the bottom, that's the internuclear distance when the bond is present. So there's our bond that's formed. Attraction between the positives and negatives, the shared electrons and the atom cores. When we break that, we're increasing the internuclear distance to a point where they're no longer considered to be bonded to each other, and that's going to require us to increase the amount of energy that was in the system by this quantity that we call the bond energy. So different bonds have different profiles on a graph like this, and here's an example that can help us understand what role the two quantities in Coulomb's law play. Here's a hydrogen-hydrogen bond. Now let's make a comparison. Here's a hydrogen to bromine bond. We can see that the bond is longer. This makes sense because bromine is a bigger atom than hydrogen, and so the electrons that make up that shared bond are farther away from the bromine than they are from the hydrogen in the HH bond. That would mean the denominator in our little comparison equation is bigger, which means that the energy required would be smaller. Another comparison, here's bromine and bromine. The distance between the particles is even larger now because now we have two bromines and both of them are much larger than a hydrogen. So the internuclear distance just keeps getting bigger as the atoms get bigger, and that decreases the energy required to break the bond. So longer bonds are weaker. Here's another comparison that we can make. And again, this one is not completely unpredictable. Here's a nitrogen single bond to another nitrogen. So these two nitrogen atoms are sharing a single pair of electrons. We can see the profile here of energy versus internuclear distance. This is a nitrogen-nitrogen double bond. So in this case, the two nitrogens are sharing two pairs of electrons. Of course, the attraction for two shared pairs of electrons is greater because it's more charge. That makes the force that pulls the two nitrogens together higher, which pulls them closer together, and that actually shrinks the internuclear distance. And here's a nitrogen triple bonded to another nitrogen. That means the two nitrogen atoms are sharing three pairs of electrons. So two things are happening here. One is the strength of the bond is getting higher. The bond gets stronger when you share more pairs of electrons. The other thing that's happening is the bond gets shorter as you share more pairs of electrons. These bond energies can be quantified, and we can estimate the enthalpy change for a reaction from using these bond energies. So enthalpy is a term that we're going to define more carefully later on, but for now we can just think about it as energy. So how we do that is we take the sum of all the bond energies for the broken bonds, that's energy that has to go into the system to break them, And then we remove from that, or subtract from that, the sum of all the bond energies of the formed bonds, because that's energy that comes out of the system. As bonds are formed, the bond energy is released as the attractive particles are allowed to come back together. So here's an example problem. What is the enthalpy change for the reaction of two H2s reacting with an O2 to make two water molecules? In order to be able to quantify this, we're going to have to figure out what bonds are exactly broken. So we're going to have an HH bond and another HH bond, because we have two H2s. And then we're going to break an O double bond O. Later on we'll figure out why that's double bonded, but for now that's off the chart. That's the only one that we have. So that's the energy that's coming in from the broken bonds. That's going to be an input to the system. The output to the system is we're going to make two waters, and each of those has two OH bonds in it. So the sum of all the bond energies for the broken bonds is going to be 2, and this is actually 2 moles, because these are kilojoules per mole quantities here, times the bond energy of an HH bond, which is 436 kilojoules per mole, plus we also are breaking up 1 mole of O double bond O bonds, which have a bond energy of 498 kilojoules for every mole. So that's the inputs. Now we're going to subtract the outputs. And we are making 2 moles of water. Each one has 2 moles of OH bonds, so that's a total of 4 moles of OH bonds, and the OH bond energy is 464 kilojoules per mole. So this is bond energy in minus bond energy out, and what's left over turns out to be negative 486 kilojoules. So what this means is when this reaction happens, more energy is released than the energy that has to go in to make the reaction start. Now let's talk about ionic bond strength. And just again, a reminder of Coulomb's law that K times Q1 times Q2 divided by the square of the distance between the two charged objects is the electrostatic force. So for two ions, that would look like the electrostatic force is equal to a constant number times the charge on the cation, the positively charged ion, times the charge on the negatively charged ion, that's Z plus and Z minus, divided by the square of the distance between the two ions. That's called the inter-ionic distance. So that means that the energy that's required is going to be proportional to the product of the two charges on the numerator divided by the distance between the two ions in the denominator. So if you're thinking about what would affect this, the bigger the charges are, the bigger the energy is, because the charges are in the numerator. And the bigger the ions are, the greater the distance between their centers, and that means the bigger the denominator, so that would decrease the amount of energy required to break an ionic bond. How this is quantified is through something called lattice energy, and this is the amount of energy that it takes to take a mole of an ionic solid and pull it apart into its ions, and the ions are far enough away from each other that they're considered to be in the gaseous state. So this equation here is kind of showing us that. Cation is cation, anion, solid, and we're separating that into cation plus, anion minus, far enough away from each other that they're in the gaseous state. And the delta H for that process, the energy change for that process, is what we call the lattice energy. So just to put some specifics to that, let's say that our cation is sodium and our anion is chlorine. So that's sodium chloride as a solid separating into sodium ions in the gaseous state and chloride ions in the gaseous state. To do that requires quite a large amount of energy, and that is called the lattice energy. So how do charges affect lattice energy? Well, by Coulomb's law, bigger charges make the numerator bigger, which means the lattice energy is going to be larger. How do ion sizes affect lattice energy? Well, that's in the denominator. As the ions get bigger, the distance between them gets bigger. That makes the denominator bigger, and that also makes the lattice energy smaller. So big charge, big lattice energy, big ions, smaller lattice energy. Let's do a comparison just to test our knowledge of this. Which will have the larger lattice energy, LIF or KBr? Lithium because it's column 1, is a 1 plus. Fluorine, because it's column 7, will be a 1 minus. Potassium, because it's group 1, will be 1 plus. And bromine, like fluorine, is a group 7, so it'll be a 1 minus. So the numerator is not going to make the decision for us here. It's both 1 plus 1 minus in both cases. Now let's look at the denominator, the inter-ion distance. Lithium and fluorine are both in period 2, so they're going to be relatively small. Potassium and bromine are both in period 4, so they're going to be substantially bigger. So the internuclear distance, that D here, is going to be small for LIF, but it's going to be much bigger for KBr. So that means that the smaller denominator in LIF would lead to a bigger lattice energy. So KBr will be easier to take apart, LIF would be harder to take apart. Here's another comparison. Which will have the larger lattice energy, KBr or CaBr2? So in this case, we already know that potassium is plus 1 and bromine is 1 minus, but calcium is 2 plus. Now calcium is going to be pretty much the same size as potassium. It's right next door to it on the periodic table. They're both in the 4th period. And bromine is the anion in both cases, so that doesn't matter at all. So the denominator, it's really about the same numbers. Not exactly, but very close. What is different is the numerator. So we have a plus 1 minus 1 in the case of KBr. We have a plus 2 minus 1 in the case of CaBr2. And so that means that with a larger numerator for CaBr2 and approximately the same denominator, the CaBr2 is going to be the one with the higher lattice energy.